We'll start in about 1 minute. Today we'll continue the test 3 review. Tomorrow is test 3. That means we won't have a YouTube live class tomorrow. But for test 3, join the Zoom meeting as early as 7:30. But try to join the Zoom meeting by 10 minutes till 8. Don't wait too long to join the meeting so we can get you started on test 3. And then more information about tomorrow's test will be sent to you later today. Okay, so we'll continue the review. We were simplifying roots and radicals. This is where we left off. So simplify the cubed root of 250 m to the 21st over 27 n to the 90th. We can use the quotient property of radicals and write the cubed root of 250 m to the 21st in the numerator, and in the denominator the cubed root of 27 n to the 90th. The denominator simplifies nicely because the cubed root of 27 is 3. That means 3 to the 3rd is 27. The cubed root of n to the 90th is n to the 30th, because the exponent 90 divided by the index 3 is 30. And in the numerator, we have a little more work to do. The largest factor of 250, that is a perfect cube, is 125. 125 times 2 is 250. M to the 21st is a perfect cube because 21 is a multiple of the index 3. So we'll rewrite the numerator as the cubed root of 125 times m to the 21st multiplied by the cubed root of 2. And you can verify that you apply the product property of radicals correctly if you multiply this radicand 2 by this radicand. You get the original radicand. Okay, now we can write the simplified answer. The cubed root of 125 is 5. The cubed root of m to the 21st is m to the 7th, because the exponent 21 divided by the index 3 is 7. And so in the numerator, 5m to the 7th times the cubed root of 2. And then the denominator is already simplified 3 times n to the 30th. Okay, we'll now look at some rational exponents. So we start, this is from section 8.3, simplifying rational exponents. Notice this it doesn't say to convert to radical form. It just says to simplify those numbers with rational exponents. So 81 to the exponent 3/2 the denominator of the exponent is 2. So that implies the square root. So we can rewrite 81 to the 3/2 as 81 to the 1/2 raised to the exponent 3. So we're just applying one of those properties of exponents. If you have a number raised to an exponent, and if that is raised to an exponent, then you can multiply those exponents. And you can easily verify that 3 times 1/2 is 3/2. But I write it this way because on the inside of the parentheses, 81 to the 1/2 is just the square root of 81. The square root of 81 is 9. And so we have 9 to the third, and 9 to the third is 9 times 9 times 9, which is just 729. And with a high-powered calculator, you can figure out that 9 to the third is 729. The next example, the number -27 raised to the exponent 2/3. The denominator of the exponent is 3. So that means we want to think of raising -27 to the 1/3, and then we'll raise that number to the exponent 2. So we're using the same property of exponents that we did in the previous example. If you multiply the exponent 2 times the exponent 1/3, you get the exponent 2/3. But on the inside of the brackets, we're going to replace -27 to the 1/3 with -3, because the cubed root of -27 is -3. In other words, that means that the number -3 to the third power is -27. Okay, then we raise the number -3 to the second. That just means -3 times -3, which is +9. Okay, in the next example, we have 5 to the 3/2 times 5 to the 5/2. And we apply one of those properties from section 5.2 earlier this semester. Since the base numbers are the same and we're multiplying, we can write the base, and then for the exponent, we add the exponents. So the exponent is 3/2 plus 5/2. And 3/2 plus 5/2, that's nice. We already have a common denominator. 3/2 plus 5/2 is 8/2. And 8/2, or 8/2, simplifies to 4, so we have 5 to the 4th. And we can simplify this further because 5 to the 4th is just 5 times 5 times 5 times 5. And this simplifies to 625. With a high-powered calculator, that won't be hard for you to figure out. Okay, the next one, in the numerator, we have 64 to the 1/2, and in the denominator, we have 25 to the 3/2. Well, in the numerator, 64 to the 1/2 is just the square root of 64, and the square root of 64 is 8. So make sure that you note that we didn't have to convert it to radical form first, because we know that if an exponent is 1/2, it means the square root of the number. And we know the square root of 64 is 8. In the denominator, it's a little more complicated. 25 to the 3/2. Well, the denominator of the exponent is 2. So that implies computing the square root of 25, and then afterwards raising it to the exponent 3, and then verify 3 times 1/2 is 3/2. Okay, so we're a couple of steps away. The numerator is already simplified to 8. Inside the parentheses, 25 to the 1/2, that just means the square root of 25. The square root of 25 is 5. And then we have the outer exponent 3, and so 5 to the third power is 5 times 5 times 5, which is 125. Our simplified answer is 8 over 125. Okay, in the next example, the directions are to convert to radical form, or sorry, from radical form to rational exponent form. So the fifth root of an expression just means to raise that expression to the 1/5 power. So we have 7x to the second y to the fourth in parentheses, and the exponent, the outer exponent is 1/5. And then using properties, one of the properties of exponents, first, think of 7 as 7 to the first. You don't have to write the exponent 1, but it might be useful, might help you remember. So then we apply that property of exponents that says we're going to multiply this outer exponent 1/5 by each of those exponents. And so when we do that, we get 7 to the 1/5 times x to the 2/5 times y to the 4/5. And that's all we're going to do on this one, because we're just converting it to rational exponent form. Okay, in the next example, we have the cubed root of 8x squared y. Converting that to rational exponent form, well, in parentheses, we have 8x to the second y, and we have the exponent 1/3. Then think of 8 as 8 to the first, and we're going to multiply 1/3 times each of those exponents. Y has an exponent of 1, so we'll get 8 to the 1/3 times x to the 2/3, because 1/3 times 2 is 2/3, times y to the 1/3. We can simplify further, because 8 to the 1/3 is the cubed root of 8, and 8 is a perfect cube. The cubed root of 8 is just 2. So our simplified answer is 2 times x to the 2/3 times y to the 1/3. Okay, we'll move on to the next page. Okay, so this is some more simplifying rational expressions. Okay, so we have in parentheses 8x to the 6th, y to the 6/5. This is all raised to the 2/3 power. So we're going to multiply the exponent 2/3 times each of the exponents on the factors on the inside. So we get 8 to the 2/3 times x to the 6 times 2/3 times y to the 6/5 times 2/3. So we have some simplifying to do. 8 to the 2/3. Well, the denominator of the exponent is 3, so that implies the cubed root of 8. So 8 to the 1/3 raised to the second, because 2 times 1/3 is 2/3. And then x to the 6 times 2/3 is x to the, I'll go ahead and write it as x to the 12/3. We'll simplify it completely in the next step. And then times y to the 6/5 times 2/3 is 12/15. And we'll simplify that in the next step. And then over here on the left, 8 to the 1/3, the cubed root of 8 is 2. And then we're going to raise that to the exponent 2. And then x to the 4th, because 12 divided by 3 is 4. So in the previous step, this should be 12 over 15, because 5 times 3 is 15. And then we can write the fraction 12/15 in lower terms. The common factor of 3 cancels, so that just becomes 4/5. And then finally, the final answer, 2 to the second is 4, so we get 4 times x to the 4th times y to the 4/5. Okay, for now, we will bypass this example B. If there's time later, I might come back to this. But let's look at this bottom one down here. We have x to the negative 2/5 times y to the 4/5, and this is all raised to the 5/3. So remember, when simplifying with exponents, in the end, we don't want any negative exponents left. So we're going to have to make sure that we handle this negative exponent correctly. But the first step is just to multiply this outer exponent 5/3 times each of those exponents. So we get x to the negative 2/5 times 5/3 times y to the 4/5 times 5/3. Then we'll do the arithmetic in those exponents. Okay, so negative 2/5 times 5/3, notice the 5's cancel. So this just is, in the next step, x to the negative 2/3. And then on the exponent for y, 4/5 times 5/3, the 5's cancel. And so this just becomes y to the 4/3. And we're just one step away from the simplified answer. X to the negative 2/3 in the numerator, this, you don't have to write it as over 1, but that's what you could write. And so x, at the moment, x to the negative 2/3 is in the numerator. That's equivalent to having x to the positive 2/3 in the denominator. So y to the 4/3 stays in the numerator, and we put x to the 2/3 in the denominator. And as I mentioned, our final answer should not have any negative exponents. So this is the final answer on this one. Okay, we'll move on to section 8.4 on adding, subtracting, and multiplying with radical expressions. Okay, add, subtract, and multiply. Well, the first one just involves subtraction and addition. When adding and subtracting radicals, first simplify the radicals if they can be simplified. And then after simplifying completely, if any of the radicals and terms are like terms and like radicals, then we can combine them by adding and subtracting. But if they are unlike radicals, or variable parts are not the same, then they cannot be combined by adding and subtracting. Each of those three radicals can be simplified further. Each one is a square root. The square root of 50y to the 7th. The largest factor of 50 that's a perfect square is 25. The largest factor of y to the 7th that is a perfect square is y to the 6th. So we will rewrite this as the square root of 25y to the 6th times the square root of 2y. And remember, you can always verify by multiplying that you're breaking them apart correctly. 25y to the 6th times 2y is 50y to the 7th. And then minus the largest factor of 98 that's a perfect square is 49. 49 times 2 is 98. And we already saw the largest factor of y to the 7th that's a perfect square is y to the 6th. So we'll rewrite this as the square root of 49y to the 6th times the square root of 2y. And then finally, the third radical, the largest factor of 18 that's a perfect square is 9. 9 times 2 is 18. The largest factor of y to the 7th that's a perfect square is y to the 6th. So we write this as plus the square root of 9y to the 6th times the square root of 2y. Then we simplify the square roots of the perfect squares. Square root of 25 is 5. The square root of y to the 6th is y to the 3rd. And so this first term, 5y to the 3rd times the square root of 2y. This is now simplified as much as it can be. In the next term, minus the square root of 49 is 7. The square root of y to the 6th is y to the 3rd. So it's minus 7y to the 3rd times the square root of 2y. And then the last one, the square root of 9 is 3. Square root of y to the 6th is y to the 3rd. And so 3y to the 3rd times the square root of 2y. When we compare the square roots are the same. Each has a square root of 2y. But on the outside of the square roots, the variable parts must also be the same before we can combine them by adding and subtracting. So everything is like the other twos, or each one is like the other two. So we can combine by adding and subtracting. So we have 5 of those minus 7 of the same. So that's up to -2, and then -2 plus 3 is 1. So we have 1y to the 3rd times the square root of 2y. This is the simplified result. Okay, the next one, let's bypass this one momentarily, and we might come back to it if there's time. I'll just mention, simplify each of the radicals first. Each one of those can be simplified. And then afterwards, if they are like radicals, you can combine by adding and subtracting. But let's move on to this multiplication. The square root of 50x to the 15th y to the 7th times the square root of 8x to the 5th y to the 13th. My suggestion is to apply the product property of radicals and write this as a single radical. The radical is a square root in this case. And then the radicand of the single square root will be the product of those two radicands. So 50 times 8 is 400. And x to the 15th times x to the 5th is x to the 20th, because 15 plus 5 is 20. Y to the 7th times y to the 13th is y to the 20th. And then we just focus on simplifying a single square root. Well, this turns out nicely. 400 is a perfect square. 20 to the 2nd is 400. And both x to the 20th and y to the 20th are perfect squares because the exponent 20 is a multiple of 2. So our final answer, the square root of 400 is 20. The square root of x to the 20th is x to the 10th. And the square root of x to the y to the 20th is y to the 10th. Okay, the next one, we multiply two expressions that are kind of like binomials. So we're going to multiply them the same way that we would multiply two binomials. So the first one, 5 times the square root of x times the square root of x, is 5 times the square root of 25. And then we're going to add 5 times the square root of 5 times 4 times the square root of 3. So 5 times 4 is 20, and the square root of 5 times the square root of 3 is the square root of 15. And then we're going to subtract the square root of 3 times the square root of 5, which is minus the square root of 15. And then finally, we're going to subtract the square root of 3 times 4 times the square root of 3, which is minus 4 times the square root of 9. Okay, we'll simplify further. The square root of 25 is 5. And so 5 times 5 is 25. The two middle terms are like radicals, so we can combine them by adding and subtracting. So plus 20 times the square root of 15 minus the square root of 15 is positive 19 times the square root of 15. And then finally, minus 4 times the square root of 9 is minus 4 times 3, which is minus 12. And we can simplify a little bit more. 25 minus 12 is 13. So our simplified result is 13 plus 19 times the square root of 15. Okay, we'll move on to section 8.5, material, dividing radical expressions. Okay, divide radical expressions. This is 5 divided by 3 plus the square root of 7. Well, the convention is to not have radicals in a denominator, like a square root in the denominator. So we want to find a number that is equal in value to 5 divided by 3 plus the square root of 7. Equal in value, but without a square root in the denominator. Okay, the way that we do that is we multiply by 1 in a particular form that enables us to get rid of the radicals in the denominator. So the form that one takes in this case, notice the denominator is 3 plus the square root of 7. So we're going to multiply by 1 in the form 3 minus the square root of 7 divided by 3 minus the square root of 7. 3 minus the square root of 7 is called the conjugate of 3 plus the square root of 7. The only difference is the operator between the numbers. Okay, and since we're just multiplying by 1, we're not changing the value of that number. We're just changing its form. Okay, so in the numerator, we multiply 5 times the quantity 3 minus the square root of 7. And 5 times 3 is 15, and then minus 5 times the square root of 7. And in the denominator, 3 times 3 is 9, and then minus 3 times the square root of 7. And then plus the square root of 7 times 3, which is plus 3 times the square root of 7. And the square root of 7 times negative square root of 7, we write that as minus the square root of 49. Okay, the numerator is as simplified as we can get it, at least for now. So the numerator is 15 minus 5 times the square root of 7. And in the denominator, we have 9. And notice the two middle terms add up to 0. Minus 3 times the square root of 7 plus 3 times the square root of 7 is 0. And then minus 7 because the square root of 49 is 7. And now we're just one step away from the simplified answer. The numerator is 15 minus 5 times the square root of 7. And the denominator is 2. And so there's nothing left to do. This is simplified. But note that the denominator no longer has a square root in it. But this number is the same value as the number that we started with. Okay, so the next one, we do a similar type of thing. In the denominator, we have the square root of x minus the square root of 5. We want to come up with an expression that represents the same value as this, but with no square roots in the denominator. Okay, so we multiply by the conjugate again, the conjugate of the denominator. The conjugate of the square root of x minus the square root of 5 is the square root of x plus the square root of 5. We multiply both the numerator and denominator by that, the square root of x plus the square root of 5. We're just multiplying by 1, but this will enable us to eliminate the square roots in the denominator. Okay, in the numerator, the square root of 17 times the quantity square root of x plus the square root of 5. The square root of 17 times the square root of x, we just write that as the square root of 17x. And then plus the square root of 17 times the square root of 5. That's the square root of 17 times 5, which is just the square root of 85. And note that the square root of 85 cannot be simplified further than that. And then the square root of x times the square root of x is the square root of x squared. Then we have plus the square root of x times the square root of 5, which is plus the square root of 5x. And then we have minus the square root of 5 times the square root of x, which is minus the square root of 5x. And finally, minus the square root of 5 times the square root of 5 is minus the square root of 25, because 5 times 5 is 25. So in this case, the next answer will be the completely simplified answer. The numerator can't be simplified any further than it already is. So the numerator is just the square root of 17x plus the square root of 85. In the denominator, the square root of x squared is x. The two middle terms cancel each other out. Those add up to 0. And then minus the square root of 25 is just minus 5. Okay, so we can't simplify any further than that, but we no longer have square roots in the denominator. That was the primary goal there. Okay, the next one, 5 divided by the fourth root of 3. Well, the denominator has a radical in it. It's a fourth root of 3. So what form should one take this time? Okay, so the radicand is 3. Think of that as 3 to the first. And we ask, what would I have to multiply by 3 to the first to get a perfect fourth power? The answer is I would multiply 3 to the first times 3 to the third, because 3 to the first times 3 to the third is 3 to the fourth. And 3 to the fourth, by definition, is a fourth power. Okay, so the form that one takes is multiply the numerator by the fourth root of 3 to the third, and multiply the denominator by the fourth root of 3 to the third. We're just multiplying by 1, so in the numerator we get 5 times the fourth root of 27. We should simplify 3 to the third to 27. And in the denominator, the fourth root of 3 times the fourth root of 3 to the third is the fourth root of 81, because 3 to the fourth power is 81. But the denominator is going to simplify to an integer. The numerator is 5 times the fourth root of 27. And in the denominator, the fourth root of 81 is 3. So we no longer have a radical in the denominator. Okay, the next one. We have 9 divided by the cubed root of 49y. Remember that 49 is 7 to the second. Since 7 to the second is inside a cubed root and it's in the denominator, we have to multiply that by 1. So what form should 1 take? Well, since 49 is 7 to the second, we ask, what would I have to multiply by 7 to the second to get a perfect third power or a perfect cube? 7 to the second times 7 is 7 to the third. So that answers that part. But we also have a factor of y inside the cubed root in the denominator. If we multiply y times y to the second, we get y to the third, which is a perfect cube. Okay, so now we know what form 1 should take. We multiply the numerator and denominator by the cubed root of 7y to the second. Cubed root of 7y to the second over the cubed root of 7y to the second. We're just multiplying by 1. So in the numerator, we get 9 times the cubed root of 7y to the second. And in the denominator, the cubed root of 49y times the cubed root of 7y to the second. Well, 49 times 7 is 343. And y times y to the second is y to the third. It's okay if you write, instead of 343, if you write it as 7 to the third, that's okay. But this is one of those numbers you should know is a perfect cube. Okay, so the next step is the simplified answer, 9 times the cubed root of 7y to the second. And in the denominator, the cubed root of 343 is 7, and the cubed root of y to the third is y. Okay, for now, let's forego this one. This one will be fairly easy in comparison to the other ones. So let's move on to section 8.6. Okay, solve radical equations. We want to solve this equation, the square root of 5x minus 7 equals 7. The variable that we want to solve for is inside of a square root. So that means we want to square both sides. So if we square the left-hand side, we're going to square the square root of 5x minus 7. We must also square the right-hand side. And when we square the square root of 5x minus 7, we're just left with 5x minus 7. And when we square 7 squared, when we square 7, we get 49. And then we just solve for x. So 5x equals 56. And then divide both sides by 5. X equals 56 fifths. And it's easy to verify that 56 over 5 is the solution. I'm not going to do it completely here, but you can sort of see what's going to happen. If you replace x with 56 over 5, then 5 times 56 over 5, the 5's cancel, so that you have the square root of 56 minus 7, which is the square root of 49, and the positive square root of 49 is 7. The next example is a little more involved. We have the square root of 3x minus 2 equals x minus 2. And since the variable that we want to solve for is inside of a square root, we want to square both sides. The radical is by itself on the left-hand side, so it's all ready for us to raise both sides to the second power. The square root of 3x minus 2 squared, and then we also square the right-hand side, x minus 2 squared. When we square the square root of 3x minus 2, we just get 3x minus 2. And then x minus 2 quantity squared means x minus 2 times x minus 2. So we get x to the second minus 2x again, and then negative 2 times negative 2 is positive 4. And then we'll just combine like terms on the right-hand side to get x squared minus 4x plus 4. Okay, then we just have an equation that we can solve. I'm looking at 3x minus 2 equals x squared minus 4x plus 4. So we'll set the left-hand side equal to 0 by subtracting 3x from both sides and adding 2. So the right-hand side becomes x squared minus 7x plus 6. And we can solve this equation simply enough. The two factors, solve it by factoring. The two factors are x minus 1 and x minus 6. And you can verify by multiplying the factors that you factored correctly. So the two solutions to the quadratic equation are x equals 1 and x equals 6. Okay, but we have to keep in mind that we're trying to solve this equation with the square root in it. So when we test x equals 1 in the original equation, replace every x with 1, we get the square root of 3 times 1 minus 2 equals 1 minus 2. So this becomes, inside the square root, 3 times 1 is 3, 3 minus 2 is 1. So we get the positive square root of 1 equals negative 1 because 1 minus 2 is negative 1. Okay, but this is false because the positive square root of 1 is 1, and it cannot be equal to negative 1. So 1 is not a solution. If we test x equals 6, replace x with 6, in the left-hand side, the positive square root of 3 times 6 minus 2, and on the right-hand side, 6 minus 2. So we'll just take this one step further. Inside the square root, 3 times 6 is 18, and 18 minus 2 is 16, and the positive square root of 16 equals 4, since 6 minus 2 is 4. This is true. That is obviously true. So x equals 6 is the only solution to that equation. Okay, in the next example, solve this equation for capital R. The fourth root of 5r plus 3 equals 3. Since the variable r is inside a fourth root, we're going to raise both sides to the fourth power. Okay, so we raise the left-hand side, the fourth root of 5r plus 3 to the fourth equals 3 to the fourth. And then when we raise the fourth root of 5r plus 3 to the fourth, we just get 5r plus 3. And on the right-hand side, 3 to the fourth is 81. And then this is a simple equation to solve for r. Subtract 3 from both sides, we get 5r equals 78. And then divide both sides by 5. R is equal to 78 divided by 5. Okay, this one is easy to verify that it really is the solution. So I'll just point out, this is similar to what we did earlier in an example. If you replace R with 78 over 5, then 5 times 78 over 5, the 5's cancel. And then you're just left with 78 plus 3 inside the fourth root, which is 81. And the fourth root of 81 is 3. That's true. So that is the solution. And then this example, 5 times the square root of x equals x plus 6. So on this one, my advice is to just square both sides without dividing both sides by 5. If you divide by both sides by 5 first, you could still make it work, but it's more work. You would eventually have to undo that division. So in this case, it's easier just to square both sides right from the start. And when you square 5 times the square root of x, I'll just remind you, when you square something, you multiply that something by itself. If you remember that, that might help you avoid one of the common mistakes that's made in cases like this. So 5 times the square root of x times 5 times the square root of x. 5 times 5 is 25. The square root of x times the square root of x is the square root of x squared, but the square root of x squared is x. And then on the right-hand side, x plus 6 times x plus 6. X times x is x squared plus x times 6 is plus 6x plus 6 times x a second time, and then plus 6 times 6, which is 36. So the right-hand side can be simplified to x squared plus 12x plus 36. And then we'll set one side equal to 0 by subtracting 25x from both sides, and we get 0 equals x squared minus 13x plus 36. And we can solve this equation by factoring. This factors pretty nicely. One factor is x minus 9, and the other one is x minus 4. So this equation has two solutions. This trinomial equation has solutions x equals 9 and x equals 4. Okay, but remember what we're doing. We're trying to solve this equation that has the square root in it. And if you check 9 to see if 9 is a solution, 5 times the square root of 9 equal to 9 plus 6. Well, the square root of 9 is 3, so we get 5 times 3. And then on the right-hand side, 9 plus 6 is 15. That is obviously true. 5 times 3 is 15 is true. So x equals 9 is a solution. When you test x equals 4, replace x with 4, we got 5 times the square root of 4. On the right-hand side, 4 plus 6, replace x with 4 this time. The square root of 4 is 2, so we get 5 times 2. And on the right-hand side, 4 plus 6 is 10. 5 times 2 equals 10. That's obviously true also. So both of those are true. So both numbers 9 and 4 are solutions. Okay, we have a little over 3 minutes, but that's enough to talk about simplifying square roots of negative numbers. Hey, if you remember the definition of the square root of negative 1, we're just using the letter I to represent the square root of negative 1. So, knowing that definition, I is the square root of negative 1, and knowing how to apply the product property of radicals and how to simplify square roots, then you know how to simplify square roots of negative numbers. So this first one, the square root of negative 49, think of that as the square root of positive 49 times the square root of negative 1. According to the product property of radicals, 49 times negative 1 should be equal to negative 49, which it does. And then the square root of 49 simplifies to 7, and we replace the square root of negative 1 with I. So our simplified answer is 7 times I, or 7i. The square root of negative 81, well, this is equivalent to the square root of 81 times the square root of negative 1. And the square root of 81 is 9, and the square root of negative 1 is I. So our final answer is 9 times I. The next one is a little more involved. The square root of negative 175. Well, we can start by writing this as the square root of 175 times the square root of negative 1. And we have to simplify the square root of 175. So the largest factor of 175 that's a perfect square is 25. 25 times 7 is 175. So in the next step, I'm going to replace the square root of 175 with the square root of 25 times the square root of 7. And I'll go ahead and replace the square root of -1 with I. And then our final step is the square root of 25 is 5. And so we multiply 5 times the square root of 7 times I. That's our simplified answer. Okay, so we'll do one more since we're about out of time. The remaining 3 are all pretty simple. Think of the square root of -128 as the square root of +128 times the square root of -1. The largest factor of 128 that's a perfect square is 64. So we'll rewrite the square root of 128 as the square root of 64 times 2. And I replace the square root of -1 with I. And then finally, the square root of 64 is 8. So we have 8 times the square root of 2 times I. Okay, so that's a pretty good sample of square roots of negatives. And we're out of time, so tomorrow I'll start the Zoom meeting at 7:30. You don't have to start the test right at 7:30, but you can shortly thereafter if you join the Zoom meeting tomorrow. But I'll send information about that later today. That's all for today.